Hello, 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 hello.
Yeah, hello.
Yeah, what happened?
No,
No,
just lost the connection for some time and we got it back.
Okay, okay, fine.
Mhm.
So, in this way, we are interconnecting, or sorry, we are writing our module to define.
Mhm.
So here, the assign is a keyword.
Mhm.
So
okay.
using Boolean logic expression, we are directly defining that module. So we know
Okay.
actually our adder is a addition of all the bits. So A plus, B plus, and C in is your carry input.
Mhm.
Okay.
So if I'm concatenating this value, then here if you are seeing my input is a 4-bit wide AB, and sum is also 4-bit wide. So C out comma sum. So this is a 4-bit result plus here C out is a 1-bit wide. So total of 5-bit result you got.
Okay.
Okay. And so structural modeling. So as we know, the structural modeling which consists of only the primitive elements and the user defined elements.
Mhm.
So they are describing the module inside in terms of the cycles. So
Okay.
if you know the exact structure and inside the logic, then we are able to use the structural modeling.
Mhm.
So which consists of a gate instance and the wire names and delay. So if you are seeing this module, we know here you are having A and B and you are having the selection line, the output will be F. You must define the input and output alone. So initially you are having three inputs A, B, selection line, and the output is F. So F comma A comma B comma SEL, that means selection. So in that, what is the output and what is the input? So those information you have to write. So output is F and input is A, B and selection line. So next,
Okay.
you are having two AND gate and one OR gate.
Okay.
In that, this is this line and this line is your internal wire, and this is also your internal wire. So you are having wires.
Three
Actually,
wires, yeah.
yeah. If you want to if you are synthesizing that model without wires, that doesn't show any warning. It will automatically interconnect.
Mhm.
So here you are having two AND gates. So this and then G1, the output will be F1 here, and the input is A, and this output is N selection line. That means NSEL. And for this AND gate, this is F2. Sorry, this is B,
Mhm.
and the output is F2, and the selection line will be SEL. So whenever you are writing the primitive, here the output must be come first.
First,
Yeah.
And next follow that you are having the inputs. So here
Mhm.
this is the N select, and here you are having A, and here you are having B, and this is select. So here you are using the comma because I am using the same AND variable for both the gates.
Okay.
Okay.
Okay. So in the case of I am using separate statement, I have to use AND G1 F1 comma A comma NSEL semicolon. Then AND G2 of F2 comma B comma select.
Okay.
Likewise, we have to define.
And the 5 is kind of a command.
No, that 5 is for describing the delay. That means after 5 nanosecond delay, the AND gate will actually work initially.
Oh,
Then
okay.
afterwards, it will automatically creating a 5 nanosecond delay for every output. That is what actually that hash working here. But in the case of synthesizing, that hash 5 will not be taking for synthesis process because this is a delay construct, that hash 5. If I want to put a delay of 10 nanosecond, then I have to use #10. But in the case of hardware synthesizing, that delay is not has to be considered.
Okay.
So if I'm that means without this #5, I'm able to write that module like that: G1 F1 comma A comma N select, and G2 F2 comma B comma select.
For design purposes.
For design purposes. Only for simulation, we are able to use that delay construct.
Okay.
And next one is your OR logic. So OR of G3 of F is your output, and F1 and F2 is your input. And finally, you are having a NOT gate. So this NOT gate, we know here the input is the SEL and the output will be NSEL. So that's what you are defining here. So you have to use that NSEL wire here. So output is NSEL. So NOT of G4 of NSEL, comma input is SEL.
So, but we didn't define any NSCL, right?
NSCL is the output of the NOT gate, right?
Yeah, but we didn't define it.
We are not defined inside the wire, but in the synthesis process, it will automatically taking for the taking as an internal wire. We don't.
So if we define
mention
like, if we define SCL as C, and we can put NC.
Yeah.
Okay.
But if it's a 2-bit wire, then we have to define it.
If it is a 2-bit, more than 1 bit, definitely we must define.
Okay.
Or
So we can write
yeah.
NOT gate first, and then we can write AND and OR gates, right? Or else we need to follow this order.
No, actually it is a concurrent statement only. So in whatever order, if you are defining your hardware, it will automatically synthesize. So that's not an issue here.
Okay.
That's the main difference between your C programming and Verilog programming.
Okay.
In synthesis, all the process are in concurrency, but in C language, it's a purely sequential language.
Yeah.
That's why we are not defining that our hardware in terms of C. But nowadays, the languages are developed that through the same C language, we are able to generate the entire hardware like Python. So that describing the netlist of our hardware, so we are able to directly instantiate that module inside the ASIC or FPGAs. So next one is a gate level modeling. So we know the model consists of a function. So if I'm designing that gate, so that delay we must that's an optional. That means here we describe that #5.
Yeah.
That gate must having a 5 nanosecond delay. But in design process, we are not able to consider that #5. So for functionality, we are having the HDL, which consists of primitive gates like NAND, NOR, AND, OR, XOR, XNOR, buffer, NOT, and tri-OR, tri-XOR, tri-buffer. So these are all primitive logics. So through that logic, we are using, that means we are describing the module. And the gate operates at a input and it produces an output. And your output must be in the first side. And next one you have to define the inputs.
Okay.
And if you are seeing this in a statement, you are able to understand. That means AND hash delay is your delay. That means delay construct. Then your instance name and how many outputs and how many inputs are there. Like you see how to define. And the instance name is also optional one. Here we describe it G1, G2, G3, G4. So for a primitive, it is not necessary. But in the case of user-defined module, you have to use the instance name must.
Okay. So for testing purposes, we'll be using the instance name, where the design we may or we may not.
Not for testing purpose. For example, if I describing in the statement, if you are seeing this one G1 G2, so after synthesizing, if I check the design, actually it will generate a modules of AND gates, and we don't know which one is G1 and which one is G2. So for that purposes, instance name will created inside the structure for easy prediction. So next one is a test module. So as I said, if I want to check a design, then there's a two types of testing is possible. One is a developing. That means one is directly feeding the input inside the simulator. By that way, we are able to check the inputs. But in the case of multiple inputs are there, then it is complicated to check all those inputs. So I have to cover at least or at most of the input combinations. That's why I'm using the test bench or test cases. So so in that you have to design a hierarchical module. Then with that you have to give the input and output port. That specification is also called as a design. Then using a separate module that has been used to feed the inputs to our design. So that is actually called as test bench. And in that, what are the inputs and outputs we defined in that, which is test cases. So this is an example test bench. If you are seeing here, you are having module design A, B, C, and you are having two input and one output. So in the test bench, what we are doing means we are not having any inputs or outputs. Actually, the input and outputs are defined as wires and registers.
Okay.
So here wire L, M, N. I defined a 3 wires, and design is my D, L, M, N. And here I am using the test T of L, M. So here test is nothing but your number of input and output. And for test module, you are having module test of Q, R, and you are having output Q and R. So here I'm input, here I'm giving the driving inputs to the corresponding L and M, because L and M is your input and N is your corresponding output. So in your test bench, we are not having any external signals. Just like a structural modeling, we are defining our input and output, but only difference is here the wire is your L, M, and N. So 3 different variables that are used for our test cases. And here, if you are seeing the test bench, here you are having a original design, and in that another hardware module which is used for generating the test cases. So in that I am giving 2 inputs and I am getting the response from the design, and that is your actual output. Based on this input, it will drive the output. So if you are seeing this model, here you are having module test bench, that means TB or T bench. Here wire, sum, carry, and the inputs are A and B. And for a half adder, here sum, carry, and A and B, and we know the sum equal to A XOR B and carry equal to A and B. So that is your actual half adder. So here I have to use the half add module, and I'm using that instantiation name, and that name is here AD, and the order what we are using here, the same in that order only we have to define the inputs and output here. For example, inside the half adder, if I'm using A and B as input in the first side, and next one afterwards, if I defining the output sum and carry, then I have to choose the same order also here.
Okay.
So A and B must be in the first first order, and next only the output will come. That is sum and carry, or else the synthesis tool or simulator tool will show an error.
Okay.
So half-fed AD of sum, carry, and A and B. So the sum and carry of two different variables, not the same of sum and C out. And test add is your TB. That means test bench AB, sum, and CO. That means carry out in module. So in that I am defining the input and output. So input is your sum and carry. In the test module, we are defining that input is sum and carry, and the output is A and B. Okay.
Okay.
Actually, that input and output are in. That means they are just changing the input output order. That means here the output is sum and carry. So in actual design, that is the output. But for the test case, using that input as a sum and carry, and the A and B as input, and it is changed as output here. So
Okay.
that variable is declared as register, REG.
Okay.
So here I am that means I am giving the input test vectors. So initial, begin, dollar monitor, dollar time, comma. Sorry, this is not a double comma, it's a single comma. Then double quote, within that A equal to percentage of B. That means A is a binary value and B is equal to percentage of B. That is B is also a binary value, that means single bit, and sum equal to percentage of B, which is also a binary, that means bit, and Cout is equal to percentage of B, that is also binary. So in that, in which order you are writing, the in that same order you have to use the A, B, sum and carry out. That means your input and the output. So initially the A and B must be of 0 and 0, and after 10 nanosecond delay, that means hash 10, B equal to 1. 1. That means after 10 nanosecond, A is always 0, B is equal to 1. Then after 10 nanosecond, A is equal to 0, sorry, A equal to 1, B must be 1. And after 10 nanosecond, B equal to 0 and A must be equal to 1. So after 10 nanosecond, I am finishing the simulation. That means dollar finish.
Okay.
Yeah.
I mean, can you show us like in an execution point of view,
Yeah,
if it's possible?
Yeah. Actually, I send you a link. You just go through that.
Yeah, we got that.
Yeah.
In that you are having a complete ISO file, so you just install that, and if you are working with means, it is easy to follow that procedure.
Yeah.
New project.
Search online, man.
Alt tab.
Google it, bro.
So always you have to synthesize your module initially. Then we want to verify the functionality through simulation.
Okay.
So after synthesizing,
Synthesize tester.
yeah, after synthesizing, you see the number of LUTs, then slices of various. So in my board,
Your
actually,
voice is breaking.
yeah.
Your voice is breaking.
Hello, did you hear me?
Yeah. No.
So actually, what we are doing means after synthesizing, you are getting the board summary. So in that,
Okay.
I'm using how many number of LUTs and inputs. So if you are seeing that you are having two inputs are used instead out of 1536 LUTs are available
Okay.
inside the board. So
Mm-hmm.
Okay.
it can be varied based on the different boards.
Okay.
So afterwards, if I'm going for simulation, so you just click on that module. Then
Okay.
afterwards, behavior check syntax. So which will verify the syntax of our module.
Okay.
Mm-hmm.
So if it is okay, then it will show the green tick mark. Then afterwards, you have to simulate our module.
Okay.
So in here, which operating system you are using?
Windows 10.
Windows 10.
Windows 10. Okay. Actually, if you are using that Xilinx ISA, there's a little issues there because in the 64-bit project, that means 64-bit OS, um, it will not execute the simulator. So you have to
Okay.
use both the 64 and 32-bit target navigator for your design.
Oh,
Mm-hmm.
So you're having two outputs, sum and carry, and two inputs of A and B. So I said
okay.
here I'm not using any test benches here. So I have to manually check my inputs. So you have to force the variable. So you have to use the right click and force constant, and you have to define the value. So 0 and B is also 0. Then
Mm-hmm.
after performing the simulation means if both the inputs are 0, then the sum is 0 and COD is also 0. And if both the inputs are 1, then the output will be 1 0. That means carry is 1 and sum is 0. So
Okay.
in that case, so sum is 1 and carry is 0. If both values are 1, so sum 1 carry 0. So this is a manually we are forcing the value to the input. Afterwards we are verifying the design. So in that case, if I want to check all the conditions, then it is complicated. So that's why we are preferring that test bench. Okay. So
Okay.
close this one. Then you have to add a new source. Then Verilog test fixture. Then maybe it is named as a TB. So the Xilinx tool which will automatically generate the test cases instantiation module. Just we have to feed the inputs alone. So
Okay.
so for the half-word module, I just creating a module. Okay. So it's a time scale. So this is a timing directory or timing directive, and here the inputs are defined as registers. Okay. And
Okay.
the output will be defined as wire.
Where?
Yeah. So in that half and design, UUT is a unit under test.
Mm-hmm.
In that sum will be declared as sum, and Cout is also declared as Cout, and the A is taken as A and B is taken as B.
Okay.
Okay. That means that dot sum is a that means dot sum is a variable that we are used inside the that design, and sum is a variable we are going to use inside your test bench.
Okay.
Just we are using the same name for our design. That's why that module is declared like that. Dot sum of sum.
Mm-hmm.
So in that case, if I want to use some other variable, so I have to use dot sum within bracket I and dot cout within bracket j and dot a within bracket a and dot b within bracket b. So if I am using like that means a b as my input and ij as my output.
Okay.
Next, we have to initializing the design. So initial, begin, because you are having multiple statements are here. So initial, begin, then end. So inside the actually that initial is a concurrent statement. In the case of hardware, we are not using initial statement.
Mm-hmm.
Only for simulation purposes, the initial will be used.
Okay.
So, but if you are using initial statement in synthesis, it shows error.
Mm-hmm.
So, so initially A and B is 0. After 100 nanosecond, that means hash 100, you you have to change the value. A equal to 1 dash, B 0, B equal to
Mm-hmm.
1 dash, B 1. Actually, it is a binary value and it is 1 bit wide, that is 1 dash, B is a binary and 0 is for 0 is I am giving.
Okay.
So initially A is a 1 bit binary 0 and B is a 1 bit binary 1.
Mm-hmm.
Then after 10 nanosecond delay, so hash 10, then semicolon, your value will be changes like that. A equal to 1 dash, B 1. So in that case, B is always 1 up to after 100 nanosecond, then 10 nanosecond. So totally for 110 nanosecond, B is 1. So after 20 nanosecond, hash 20, B is equal to 1 dash B 0, right? So that double slash for comment.
Comment.
So yeah. And the same for multiple comments you have to use slash asterisk then asterisk slash. Okay, so this is for multiple comments. Then afterwards you just save your module. Next you just simulate the same thing. So you can check your syntax, then you just run your model. If already simulator window is open, means it is you have to close that for every simulation.
Okay.
So if you are seeing that, you will see the output. Actually, so initially it is the sum and carry are in don't care condition. Then afterwards, after 2 nanosecond delay, your process is started. So here this value A is 0 and B is 1. Then after 100 nanosecond delay, A and B are both are 1. Yeah.
Yeah.
Afterwards, A is 0 and B is 1. Then A is 1 and B is 1. Then A is 1, B is 0. Then afterwards, finally, the simulation will be completed up to 1000 nanoseconds. For A is 1, B is equal to 0. By default, the simulation is going up to 1000 nanosecond. So within that, how many inputs I give, so within that particular period, that will be changes. So instead of this one, if I'm using 200 nanosecond delay, you can see the clear view. I just close again and so did you see the simulation that time period is varied rather than the previous simulator window? So actually
Yeah.
here it is a 200 nanosecond delay. So initially it is a 0, then both are 0, then next one is a A is 0 and B is 1, and here A is 1 and B is 1, and here A is 1 and B is 0, and the corresponding output
Okay.
is also changes here.
Mhm.
Okay.
Afterwards we are not giving any input, so up to 1000 nanosecond the same values will be retaining there. That is the purpose of actual register. So whenever we are disconnecting the wire, still the value is present inside the register. That means the previous value is
Okay.
retaining there. But in the case of wire, if you are terminating that element or net, then it automatically disconnect from the terminal. So there is no information is present in there. So maybe which is in a condition of X, that means don't care condition, or in a high impedance
Okay.
state. Now see this program. For in this case, I'm using two modules for the test bench, and and here initial begin dollar monitor, and if I'm using that dollar monitor, then the simulation output is shown in the command window. That's why the dollar monitor is used here.
Mhm.
So initial. So now see the command window. So we are having initially A is 0. For the 0th, that means 0 nanosecond, A is equal to 0, B is equal to 0. So the sum is in don't care condition, and COT is also don't care condition. So for a 2 nanosecond delay, A is equal to initialize to 0 and B is initialized to 0. So sum is equal to 0 and carry out is equal to 0. After 2 nanosecond delay, A equal to 0, B equal to 1. So sum equal to 0 and carry out is equal to 0. After 202 nanosecond delay, A is equal to 0, B equal to 1. So sum equal to 1, carry is equal to 0.
Mhm.
After 4 nanosecond delay, A is equal to 1, B equal to 1, sum is equal to 1 and carry out equal to 0. After 402 nanosecond delay, A equal to 1, B equal to 1, and sum is equal to 0, carry is equal to 1. After 6 nanosecond delay, A equal to 1, B equal to 0, so sum equal to 0, carry out equal to 1. After 602 nanoseconds delay, A equal to 1, B equal to 0, so sum equal to 1, carry is equal to 0. So in this way, we are monitoring the signals inside the simulator.
Mhm.
Because rather than checking the that waveforms, we are easily understood what is the input and output we got. So that's why we are preferring this monitor signal.
Mhm.
So in this way, we are verifying the functionality through test space simulation. So so this is the purpose of monitor signal. Actually, it prints a string after execution. Then afterwards, whenever the value changes, that value has been displayed inside the monitor. So only one monitor is active at any time, and the after the completion of simulation, it will shows the output. And this is the output what we got after simulation. Here for this program, your delay will be 10 nanosecond, but in my program I gave 200 nanosecond delay. So that's why the delay time, based on the delay time, your output response also changes. So if I using the dollar finish statement, the that means the simulation will terminate after the particular time period. That's why we are using some kind of hash 10 dollar finish. But the statement is
Okay.
not necessary. But in the case of clock, if I'm using, so for a particular period, how to terminate for a combination circuit, it is not a problem, because definitely after 1000 nanosecond, it will automatically terminate my simulation.
Okay.
But in the case of clock, actually it will automatically, um, we are giving the clock input of, with the forever loop. So what it actually happens means it will continuously simulating the module. So for a particular time period, I have to terminate the module. So in that case, I'm using that dollar finish statement. So if I am using this dollar finish statement after some particular time period I have defined here. So for example, after 600 nanosecond, I have to complete my simulation, means as 600 dollar finish statement I have to use. So if I use that statement, then automatically, it will terminate my simulation after 600 nanoseconds. So the function of the tester or test module is to generate the test cases. So here if you are seeing this program, here at time 0, A and B both are set into 0. After 10 nanosecond or after 10 time units, B is initialized to 1, and after 10 nanosecond, A is initialized to 1, and afterwards, after 10 nanosecond, B is again initialized to 0. Then afterwards, it is terminate the simulation. So total of 40 nanosecond, your simulation will be completed. So so that number of comma which actually specifying the spaces. So
Okay.
percentage of B is a binary, and you are having a hexadecimal, decimal, and octal. So B, H.
I have one question.
Yeah.
You have sent all these PDFs to us, right? All these
Yeah.
PPTs.
Yeah.
Yeah. Yeah. Then fine. Yeah.
Yeah. That video as well as the presentation as well as that PPT, I will give it to you. So that's not a problem.
Okay. But they have sent us one
One.
complete file. They in that we have more PPTs and Word documents.
You can prepare that also. But actually, yesterday only I uploaded that videos in the Google Drive. There's a little issue in the drive, so that's why I didn't upload it. So definitely they will share you today itself. I will inform to them.
Okay. Yeah.
Okay.
I mean, what you
Thought us
thought.
to know.
Pardon me?
Actually, we were trying to write down the programs that you were showing, but you're moving the slides pretty fast for us to write it down. So we were thinking that if these videos were being saved and sent, it
Yeah,
would be really great.
that will be given to you. So don't worry about that. So you can just go through that. If you're having any doubt, means you just feel free to ask me. So that's not a problem.
Okay.
Whatever the doubts you are having.
Okay.
And that videos which contains a presentation as well as the PPT, I will give you in separate.
Okay.
That's all.
I mean, that video means that you are recording what we are
what
doing now, right?
what I am taking, yeah.
Yeah. Yeah. Okay. Then fine. Yeah.
Then I send you a link for a software, and in case of installation, if you're having any issues, means you just ask me. Actually,
Okay.
that's only one issue. You have to set the environment variable for the, that means for installing the Xilinx to work with
But
yeah. But
we already, I mean, like I already installed the.
Xilinx 2017.
then it's fine. The working procedure is same.
But
Yeah, it's actually a virtual machine, and I'm able to write down the codes in the virtual machine. That's fine, right?
Virtual machine in the sense, actually now, but I sent a link for your for the software, which is a complete package. So you just install it inside the Windows, and it is easy to mount that.
I have this one.
It is a
yeah, we
separate.
got
Uh,
Linux package. It's opening the Linux window separately, and then in that we need to program.
no. That virtual machine is then which is made up of only for Verilog series boards and SoC purposes.
Okay.
So that is not needed. I will send you a link. You just download that software from the Google Drive.
Yeah,
Yeah,
it's
yeah.
like 6 GB file. I have downloaded
Yeah,
it.
that's a ISO file. So you
I mean, I was just,
install it.
curious because even we can implement the programs in here, right? So it will be
Yeah,
an opportunity.
yeah, definitely. You can, in that case, you may just try by yourself, and for digital circuits, you just use the digital design from Maurice Mono. Which is
Maurice
a
Morris
Man.
man.
Maurice Mono, which is a good book for thorough the digital logic as well as a Verilog design.
Okay.
And refer the internet too for programming and synthesizing the module. And in that case, if you're having any issues, means you just ask me, and I will try to rectify that.
We have the Verilog HDL from Samir Palinkar. We have
Ah,
that book.
and that is also a wonderful book. So you just follow that. But for Samir, that some of the processes and they are described in that book is a little complicated one. So if you design, if you are thorough in basics, then it is easy to define the modules, and you are able
Okay.
to. That means you are able to recognize the um, program what they are written.
Mm-hmm.
So this is a description of a monitor signal. So how many commas are there that will actually define the spaces, and I said the percentage is a variable. That means the percentage is a the data construct which is in a form of binary or hexadecimal or decimal. So that kind of information, and the number of the input and outputs are declared afterwards. And dollar display, which is similar to your printf statement inside the
Mm-hmm.
C. So, so this is the major difference between the structural and behavioral modeling. So
Okay.
structural modeling, which consists of a primitive gates and wires, and which is mainly based on the structure of our logical netlist. And, and we are always preferring the structural modeling. Why means we if we know the exact functionality or logical design of our module, then we are able to describe in the complete module, which is very much easier. That's why we are preferring that HDL language rather than C programming, because which is a complete which is a sequential language, C. But in the case of hardware, we know if the hardware is working in which order, in that order only we have to define the functionality. So this is a major difference between your C programming as well as HDL languages.
Okay.
Okay, then in behavioral modeling, based on the procedures, almost like a C language, and we are using the same inputs and output inside the module, and we are using the module name, and based on that we are describing the module based on the procedure and the algorithm,
Mm-hmm.
and we are not using the gates to connect it. For example, if I want to design a multiplexer, you just consider you are having 4x1
Mm-hmm.
multiplexer. In that, two selection lines are there and one four inputs are there. in the case of structural modeling, what I am doing means I am just describing the hardware functionality. That means you are having how many AND gates or NAND gates are there, and how many NOT gates are there, and how many input and outputs are there. So those informations are describing in the structural modeling. But in the case of behavioral model, what we are doing means in if selection line is 0, then output D is equal to A. Else if 1, then D is equal to 1. So likewise, I am describing the model based on the if statement or case statement.
Okay.
I am describing the procedure or algorithm. So that is the difference between your structural and behavioral model. So why we are using the behavioral model in the sense, actually for writing the test, it's hard to describe the entire hardware. So for high level specification, we are using the test bench to define the module. For the test cases, for example, if I want to generate a test vector for more than 50 inputs, then I am using the for statement for I equal to 0, I equal to I plus 1. Then I have to I is less than I plus 5. Then I equal to I plus 1. Then I am describing A of I equal to percentage of I. Likewise, I am describing the test cases for the logical model what we have designed. So this is a summary of our today's lecture. Actually, we have seen the different levels of abstraction. So the another one modeling is there. That's the data flow modeling. So except the behavioral and structural, in data flow modeling, we are just describing the Boolean logic expression with the assign statement, assign keyword. So now we know how to define the models with 3 different levels of abstraction, and you are having 2 types of descriptions of that. And that means the description which actually describe your hardware, and the simulation which will verifying the design. So that's why in the description we are describing actual hardware in terms of behavioral or data flow or structural modeling, and in the simulation we are using a test bench or test cases to describe the functionality of our module through the inputs. Then there is, we are describing the hardware concurrency through the structural modeling. That initial statement which is used for inside the test bench to describing the input functionality in terms of hardware concurrency, and that initial statement is used only in the simulation, and that is not used inside the actual design. And that initial statement for concurrently executing the input test vectors, and instead of initial we are using always a statement inside the hardware element. That means actual statement, because based on the input how the output will change. That's what actually defined inside the always such statement. Then the ASIC foundry support is also there for describing the Verilog module. For example, if I design any module using hardware description language like either Verilog or VHDL, then we have to use the technology, that means 180 nanometer or 45 nanometer technology for foundry foundry setup. That means after for fabrication we are generating a netlist. It's a purely technology independent netlist after synthesizing. Then we are mapping that technology netlist to the that means after synthesizing that netlist to the technology. So from that we are getting the actual GDS2 file after place and route, floor planning, So after doing all those steps, we are generating the GDS2 file. So if we are given that GDS2 file to the foundry, we are getting our hardware module for fabrication.
Oh, okay. So GDS2 file, like it's after layout we make it and that we give to the foundry.
Yeah, after generating the layout, we are getting the GDS2 file. Actually, that GDS2 it consists of a number of layers we are used for designing the hardware.
Yeah,
And
metal layers, okay.
metal layers and the polysilicon. So those informations are embedded into the GDS2 file. And it's not a human readable file.
Okay. And I had one more, like, what's the difference between always at, like, sensitivity list block and assign statement?
Always at and?
Like, you showed it earlier that we keep the sensitivity list, like,
Yeah.
always at start.
Yeah.
So what's the difference between that and assign statement?
Always at in the sensitivity list. Yeah.
The next slide. Yeah.
Actually, in the sensitivity list, I declared here at pause edge of clock. Maybe in some synthesis construct, we may use asterisk symbol, always at asterisk. Actually, in the sensitivity list, actually it shows the number of inputs. For example, here always at pause edge of clock, based on the clock pulse, it will changes the output, irrespective of the reset input. But in the case of, for example, if we are taking here, in that case, I'm using three inputs A, B, C, in. So if I am declaring here, what I am using means always at A, comma B, comma C, or A or B or C.
Okay.
So whenever the input changes, that means in either case A changes or B changes or C, then automatically that change will replicate in the output side.
Okay. And like, if you go back to the previous slide, which had always at pause edge of clock.
Yeah. Because here the only based on the clock pulse, the output will change.
No, like you told earlier that like inside pause edge of clock we'll use non-procedural instead of procedural.
Non-procedural. Non-procedural statement only when we are using that assign statement.
Okay.
In that case, we are using non-procedural. That means less than or equal to.
Okay.
But
okay.
In that case, but if you are using that procedural non-procedural, most probably we are using inside the always at statement. That's a procedural statement.
Okay.
In some cases only we are using that non-procedural, but that is also not much difference for the hardware.
Okay.
But in the case of assign statement, if I use the less than or equal to statement, then which is not taken by the synthesis tool, and if I am using that less than or equal to here, the hardware is working similar to this statement.
Okay.
So
okay.
So the basic difference is the always is like predefined functionalities over there, whereas assign we can define the functionalities in there.
Yeah, always that is a keyword here.
Okay.
And assign is also a keyword, but always at whenever we are preferring means actually, if I'm using a case statement or looping statement assignments, for that cases we are using a always at statement.
Yeah. Got it.
Okay. Case while, but here we are not having while do while loops, but in the case of while, that means if else statement and case statement, because if I want to define the multiplexer functionality, then I have to use the if else statement here. For example, like this, you just consider this program.
Whenever you are using any condition, we need to use always. If always at the beginning. I don't know.
A comma B and X comma Y, and here input is A and B and output is X and Y. If I'm using if statement here, if X equal to 1, X equal to 1, then B is equal to Y, else A equal to X. So in that case, if I'm using always at statement, here we are not declaring any clock pulses. So my behavior is entirely depends on the inputs A and B. So whenever the input it changes, then the output will also change. So actually, if I am giving the input, then actually it is a level triggered. Based on the levels of A and B, it will automatically changes the output. In the case of clock, if you want to use the positive or negative pulses, that's why we are. That's the difference between that declarations.
Okay.
So if I synthesize. It shows the error. So actually, whenever you are using the variables, that means input and output, you have to declare the register variable, because whenever I am using the always at statement, I have to use reg. Okay.
Okay.
Because it's a procedural construct.
And you don't need to use the begin and end statement over here.
And like you are assigning value.
Yeah, because there are multiple statements, so I have to use the begin and end.
Okay.
And you are assigning values to the input, like B is equal to Y. It should be Y is equal to B.
Output is Y. Sorry.
So you are assigning B is equal to Y.
Correct. So if we are after synthesizing, so it will form the latch.
Okay.
So like this, we are defining the module. So only case you have to understand, if it is always a statement, that variable comes at a register that forms a memory element. And in the case of assign statement, actually it is a concurrent statement. So for assign statement, we are not using that register. For example, you may see this example, the same one. Assign. Here I declare the register. Okay, so assign x equal to a equal to x and assign b equal to y. So it is a symbol buffer. So if I am synthesizing, definitely it will show an error, because which is a register is declared here. So inside the all that statement, it forms the memory.
It forms a latch where
memory, that means latch or flip flops. That's why we are
Okay.
preferring the behavioral modeling for state machines or clock synchronized machines.
Okay.
Synthesis.
In the console, it will shows the process what is carried out. So if you are
Okay.
seeing the actual area power delay, so those informations are concern that synthesis. So you must know the number of LUTs and flip-flops. Here it is a simple buffer, so it will not take any LUTs. Okay, if you are seeing here,
Okay.
you are having only number of slices and input-output bounds. So here total of four, we are having four variables. So four inputs and outputs are taken here, and if you see the some synthesis report, it will show the uh, number of LUTs, flip-flops, and what kind of board we chose for our design. And this is a complete FPGA and CPLD software.
Mm-hmm.
So the speed rate will be -5, and the combinational path delay, which is a 6.305 nanosecond. So this is your critical path delay.
Okay.
So critical path in the sense the longest path between your input and output. So this is the maximum delay of our circuit.
Okay.
Okay. So that's a delay which can't exceed practically.
Yeah. This is the maximum delay. That in the sense, if the delay is maximum, then the speed will be reduced. The frequency of my design is 1 by 6.305 nanosecond. That's the actual clock frequency of your design. Beyond that speed, we are not able to achieve.
Okay. Okay.
Okay, so the main objective is to you have to reduce the area delay as well as power consumption. And if I'm implement design in the sense, then the post processing happen. If you are connected that board means you are able to verify the functionality of a design in the FPGA board. So after
Okay.
when the process is completed, then automatically it will implemented our design. Then we have to program that design through the generate programming file. So it will generate a dot binary file inside the location that we have created the project. So if you are seeing, you are having number of files that has been generated by the synthesis tool.
Okay.
So after
So
yeah,
I have one general.
pardon me.
You said they are like. I have a general question regarding
Yeah,
the test bench thing.
yeah,
You said there are like many job opportunities in test case
yeah,
scenarios rather than development design, right?
yeah.
So what is the exact job over there? Like they will be giving us a kind of a developed circuit, and we'll be testing it with the simulation and reporting the errors and stuff to the
Yeah.
developer.
Yes, sir. Actually, what they are doing means now for test benches they are using a system Verilog. It's a system Verilog
Okay.
and UVM constructs. So you are having a number of test cases and test modules are there. What they will give the IP design intellectual property, and in that we know the functionality of the design, and inside the code we don't know. So what we want to do means we have to generate all the test cases and all the possible inputs, and you have to verify the functionality of a design. Then
So
after
how we can get,
how we can
yeah, getting the test cases, like we'll be figuring it out, like just considering it's an AND gate, so this would be a test case for it, and this is gate, so the test case for that, or there's a predefined functionality of how we define these things.
and that's a predefined the functionality they will say. That means the equations are already given by themselves in the description itself. The module description, they're describing the functionality and specs they will give you.
So
And they will give the test. That means they will, for example, for 8-bit design. In that you are having number of functionalities are there, then addition, multiplication, division. So for all the cases, you have to generate the test vector through Perl scripting languages. Then you have to feed that to the simulator like Mentor Graphics, Model Sim, Costa Sim. Then afterwards, we have to verify the functionality, and that output has to be analyzed through the scope.
so we will be writing a code,
Yeah,
right?
you have to write the code. That means that scripting language to generate the test cases, and how many test
Yeah,
cases you have to do, because more than millions of IP cores are
there, yeah.
defined the functionalities inside there. So you have to describe the all function. That means describe the test cases for all the functionalities, and you have to verify.
I mean, let us say for an example, there was a circuit like for like a cell phone circuit.
Uh,
So we'll be writing a test cases regarding the processing part and then the signaling part and
yeah.
the other functional.
All the functional processing elements are digital components. Nowadays, they are analyzing the test cases for analog components too.
Okay.
But the only
But
thing,
actually, when you showed us, we got a test bench for the design, right?
yeah,
So is it not the, would there not be a test cases for the design? Like if any person designs it, they will already be getting the test bench, right?
no, not like that. If I am completely, but in the case of industries, what they are doing means they are developing the IPs alone. Okay,
Okay.
the design team is separate and testing team is separate. And in the customer requirement, they are developing an IC, in terms of IPs, and they will in the most cases they will check and given to them. And
Okay, so the test cases will check the customer
yeah,
requirements,
based on the
IP
requirement,
that we have.
yeah, IP we have developed. Then we are checking that IP through the that means separate team. They will check the functionality of that IP.
Okay.
Because nowadays the tools are very much automated, and verifying the functionality is a little bit tedious one. Testing.
Okay.
So the opportunity for VLSI testing is very much more when compared to the design. But design is also a better field.
Okay.
So after generating the programming file, you are having number of files that has been generated inside that project directory. And if you are seeing that dot bin file, this is the bit file is your actual programming file after generated the implementation. So for this module, I am getting this binary file, bit file. So if I implement this bit file inside the FPGA, then we are able to verify the functionality in the hardware. So this is the actual bit file, and we are not able to read that file. Only that board will read the file.
So once we write the test cases, we load this bit file into the board.
Actually, that test cases we are not, manually. If you want to check the functionality, then we have to dump that bit file inside the FPGA, and we have to toggle the input and output based on the input we have.
The specified outputs are not
inside that. Yeah.
Oh, first we'll be checking it virtually. Then the next level is
checking in the board level.
Okay.
Yeah. So next we are going to see about the hardware modeling. Actually, what are the ports and implementations are available, and what are the primitives are there. Then how we are describing the styles, whether it's implicit or explicit. Then structural connections and hierarchies, and in which methodology we are always using the design. That means both the approaches are okay. That means whether it's a top down or bottom up approach, and how we are hierarchically arranging the designs. Then how the instances are interconnected. Then how we are performing the synthesis process. So here, if you are seeing the same AND module, AND gate, it's a, see here, it's not a
half
the same half adder which has been described using like that.
Okay.
Here, if you are seeing, this is a complete structural modeling. So this is an explicit structure of an statement, and here it's an implicit assignment. What we are doing is we are just adding the two variables a and b, and we know the carry and sum. We are concatenating together, means we are getting the same output of half adder.
Okay.
Yeah.
And here what we are using means instantiating two different modules. So and underscore half. So we are using this module name. So and underscore half. Here we declared sum and carry first. So you have to declare here the same thing first. So w1 w2 as the input, comma a comma b, and underscore half m2 sum w3 w1 comma cn. So w1 w2 are internal wires, and sum is a output, and w3 is another variable. And the carry output that we have to generate. So w1 is my output of this module. So w1 comma cn is the external input.
That means
Yeah.
we are using that add half is there, right?
Yeah.
Fourth line, like that's all. That's a function we have written before.
Yeah. This is that module.
Yeah. Yeah.
Okay.
This module we are using there.
We are implementing it over there.
Yeah.
Yeah. Add half is the function that we have written.
That's a simple half adder.
Yeah.
X or a sum equal to a x or b.
Yeah, I got it. I mean, the add half is the part that we are writing. Whatever is it in there.
This slide, we are using the same as add half in the next one.
Next one.
Right?
Add half 2. This is a alternate module name.
Okay.
Oh, okay.
This is you just the same, but the functionality is one and all same for both the modules, but the assignment is different. Here we are using a structural modeling, and here you are using a data flow modeling.
Okay, so data flow modeling is easier in a shorter level, right?
Shorter level, yeah, it is easier. But if you want to use the elaborate model, then you prefer the structural modeling, because if you know the exact hardware functionality, then it is easy to understand the module.
Okay.
But for declaration, which is very much easy compared to anything. If you know the functionality of a
Yeah.
Boolean expression, then it is we can write the expression using the assign statement. For
Yeah.
example, if I am using, we know what is the functionality of full adder A XOR B XOR C. Then you can use assign sum equal to A XOR B XOR C likewise. For example, here.
Okay. I do have one more question.
Yeah, same.
In the design level, can we design something in Verilog or we can't design? I mean, like fabrication of a transistor or kind of a thing.
Actually, transistors are already fabricated. We are not using that order description language to fabrication of transistor. Actually, we are mapping that layers. That means actually we are mapping the layers with the hardware description language. We are not generating the transistors.
But yeah, but I mean, like, for example, if you want to create a transconditional amplifier,
Yeah.
so there's a particular way to design it, right? Like,
Yes.
a
Actually, for
yeah,
that's an analog device.
yeah.
That hardware
Can we,
description language is a purely for digital design alone.
okay,
If you want to design a transconditional amplifier, so likewise, if you want to design, then we have to go for a that spice simulations or transistor level
okay,
design. And another one mixer level language is there. I mean, that means mixer level signal language.
mixed level signal language.
Yeah, mixer signal language. That means
Okay,
that we are describing both analog and hardware, the digital components on the same IC.
yeah, that's what we discussed yesterday, right?
Yeah, that is actually that's a mixer Verilog and the VHDL both are having the same thing is there, but the construct is little bit different.
Mm-hmm.
So actually that elements are used only inside the spice tools and spice languages.
Okay, yeah,
And similar to the that FPGA, you are having field programmable analog arrays also there, which is purely made up of analog devices, and in that we are able to program the analog devices alone.
okay,
So for your digital functionality, and your Verilog and VHDL is used only for designing or describing the digital components.
uh, like processor and stuff.
Yeah. If you want to describing the that means analog components, then we have to use Verilog AMS.
Okay,
Verilog AMS in the sense Verilog analog and mixer signal design language. It is also a same similar construct of Verilog, but instead along with that we are using some of the power supply, ground, and CMOS devices inside the Verilog statement.
okay,
That's a separate one, and you just go through the netments, you are finding similar terms, but the simulator tools are very much costlier
okay.
for doing that for analog AMS design.
Mm-hmm. But LTSpice is a free software, right?
Yeah, LT-Spice is a free software, but that won't
Okay.
support AMS.
Oh, it doesn't support mixed signals.
Mixer signal that only supports a spice language.
Okay.
So if you want a spice modeling, you can prefer that LT-Spice. And Verilog AMS, the cadence which support Verilog AMS. Then afterwards, if you are seeing Tanner EDA. So,
Okay.
so those tools are supporting that Verilog AMS. Tanner, which is offered by Mentor Graphics now. That means if you are preferring to go for a layout,
Yeah.
then you have to study that AMS language. But nowadays, full of we have to made only through the transistor level design. So that means we have to use the transistors to connect those devices, and we are manually using that GUI to connect all the devices. Then you have to generate the layout. Yeah, most probably you are not preferring that Verilog AMS and VHL AMS. Rather than they are generating the layout through the schematic design. But still in the industry standard they are having the AMS, but in academic purposes very much few only they are using for their designs.
Okay.
So if you are seeing that for a full ladder, you know the x equal to a XOR b XOR c and y equal to a and b plus b and c plus c and a. So you have to use the brackets to separate the functionality, because we don't know which one is having a higher priority. So here x and y is an output and a b c is my input. So which will actually create our full adder functionality. So if we synthesize the design, so better it is a simple design. So we know we don't want to verify. We are not able to verifying the design. But in case of a complex design, we must verify the design through simulation. Okay.
Okay.
So if we see the design, we are having AB plus BC plus CA, and this is your carry, and the sum will be AB, and this is your XOR functionality. So it's a black box. So A XOR B XOR C. So likewise, which will generate a full adder module. So if you know the Boolean expression, we just assign the statement. In that we are able to generate a hardware module, or else we have to use a structural modeling if you know the internal functionality of a design.
Okay.
Okay, and for example, and we can take this module. So you are having multiple modules like that.
Okay.
And all those models you are having a number of and non NAND gates are there, and just interconnecting all those modules, and so what I am doing in this sense, I just want to connect, and all the modules which consists the same logic gates. If you consider like that, and the output of this one will be coming on this side, and you are having three inputs. Output is on this side. And here my input is AB, and and the final output of this gate will be S1 and S2. Okay, va?
Okay.
Actually, this is this is one module, and this module consists of one NAND and NOR gate. you just consider. Okay.
Okay.
Which are having two input. This is A and this is B. And the modules which are all consist of the same logic gates and same input and same output. So here it is A, B as an input and S1 and S2 is output, and S1 is A NAND B and S2 is A NOR B. Okay.
Okay.
The module which consists of 4 logic gates. So how I would connect means, we just consider this one, a module, and the logic gate will be and EISA example, and you are having output as S1 comma S2 and input as A and B.
Okay.
And input A comma B and output S1
S1.
S2, assign S1 equal to A NAND B.
Can we discuss this tomorrow?
Yeah, fine. Okay, fine.
Yeah.
Okay. Time is more than okay, fine. Okay, if you're having any doubt, means you just ask me, and
Sure.
we'll continue the same thing on next class. And don't forget to install that software. And if you are facing any issues, means you just convey. Okay,
Sure. Yeah. Thank you.
yeah. Thank you very much.